petrography. So everything is here, and the main thing is that it is just, I know all of you are knowing it from our very undergraduate days. We are studying it, so nothing new to you. Nothing new. It is just the refreshment of your memory, I should tell, and just keep in your mind that what is the what we have read earlier, and what is the now the trend is in sedimentary petrology. What is the trend? What you have to do better, to publish some in some national international journals. What to do? That is the I will come after it, after in the last session of my lecture. But the basics, the things that we have already studied, it should be here. And the objective of this training is that you know everything, but to refresh your memory and to keep you abreast, that you should apply in your day to day and your this official work or your in the field work every day. So that is the main objective. So before after that, I am coming in my first slide. We know that rock cycle. Rock cycle, every geologist is knowing, nothing new, that the mother of any rock is your magmatic rock. That means igneous rock. So from igneous rock, metamorphic rocks will be formed. From igneous and metamorphic rocks, both your sedimentary rocks will be formed, and your sedimentary rocks is the ultimate product of all the other rocks. Yeah, an earlier sedimentary rock that may be again recycled, and then a new sedimentary rock may be formed from that. So the igneous, metamorphic, earlier sedimentary, every rock is there, which will be weathered and eroded, and ultimately give rise to sediments, which will be buried and lithified to give you the new sedimentary rock. So it is actually the rock cycle going on. Now, the relative proportion of the rock groups, if we study, we can tell that sedimentary rock, it is in just you see here that the crustal volume. What is this? This is your igneous rock. So crustal volume, only a minor part is there in the crustal volume taken by your sedimentary rocks. But if we come to the land surface area, in the land surface, the major share is given by almost 75% share is given by your this sedimentary rock, and only 25% share is given by your igneous rock. So this is drastically opposite. When we calculate the total crustal rock, then sedimentary rock is very, very less, and the magmatic and your these metamorphic rocks are much more, but here it is on the land surface, it is very less. So this is the proportionate distribution. And for the sediments, to form the sedimentary rocks, we know the main thing is the sediments. The sediments should come from weathering and erosion of the other rocks. It will be transported by different transporting agencies like water, wind, and it will be deposited ultimately in basins, and ultimately it will be lithified by compaction, that is squeezing out of water, and diagenesis. Day before yesterday I told you that. So after compaction, that is diagenesis, and after that the stage is your metagenesis. Metagenesis is not coming here. So transport by and when it will be transport, each and every these transporting agencies have their own signatures on the sediments, and those signatures we study as sedimentary structures. So so uh, sedimentary structures. So these sedimentary structures are there to study that which agencies have been acted upon the sediments, and in at what environment. So that is the main thing. Then burial and lithification. So everyone is knowing that. So this is the primary things for forming a sedimentary rock. Now the types of the sedimentary rock. I know you know all these things, but still have a look because just to reconcile the previous things. So clastic rocks, clastic sediments, it is formed by the weathering and erosion of the pre-existing rocks. So what is your clastic rock? Then weathering can be physical or chemical. Then erosion and subsequent transportation, already I told you. And another one is there, that is the biogenic and chemical sediments. That means precipitated, biochemically precipitated rock or chemically precipitated rock. So one is your clastic and another is your biogenic or chemical sediments. So these are the main sedimentary that is the rocks over land surface. Barring it, some few are there. They are the volcanic clastic sediments and rocks, and others are some carbonaceous sediments and evaporites. So these are very less, and with less than 5% share they have covered within the total sedimentary rock. And volcanic clastic, you know, that is volcanogenic sediments. We know the volcanosedimentary rocks. It may be your aeolian, or it may be your stream sediments, and that is the sediments with your volcanic materials that has been preserved along with the sediments. Mostly they are the tooth-like substance. So these are the main two varieties, clastic and non-clastic or chemical. So mineralogy of the sedimentary rocks, it comes, that is the clastic sediments, you know, it is quartz, feldspar, mainly clay minerals and rock fragments. So main two things are there, three things are there, quartz, feldspar and rock fragment, based on which their names are coming. It will be shown later. And with this, the clay minerals. If it is calciclastics, then with this clay mineral, some calcite or dolomite will be there with association with these clay minerals. But the main is quartz, rock fragment, and feldspar. So these things are very important. Then your carbonate or biogenic sediments. It is either aragonite or calcite based on the pressure, temperature, and pH distribution. It will demarcate you whether you will get aragonite or whether you will get calcite. So this is very important. That is, the environment suggests that whether you will get aragonite or calcite, but those are basically the carbonates. And the chalcedony or flint, chalcedony silica, this is occurring as subsidiary along with the calcitic sediments. And the next one, very less, but it is very important in our mineral oil basis also, that is evaporite, chemical sediments, that is the halite, gypsum, anhydrite, all these things. And with this, the dolomite. This dolomite also, it may be formed by the replacement of the calcite through dolomitization. This is another. This is coming under your evaporite, but basically this is of calcite and it will be changed over to dolomite. So the mineralogy of the main sedimentary rocks are like this. Now, coming to the sedimentary petrology, one of the main important factor is your petrography. So, petrography is the first hand tool to suggest that what we are studying, which rock we are studying, which sedimentary rock we are studying, and to classify, to describe the sedimentary rock, we know from our very undergraduate days that it must be described with some of the parameters. Those parameters are very important to describe a sedimentary rock. Those who are in some exploration exploration activities, associated with some exploration activities, or in the drilling projects, you know that you have to describe each and every rock in your logging report. When you will log a drilling material, that is a core, so you have to describe the core with respect to some parameters. May it be metamorphic, may it be igneous, or may it be your sedimentary. Each and every rock has its own parameter or characteristic that you have to describe through them. So, what is the purpose? Purpose is that if I know, if I describe, just apart from the sedimentary, if I describe a rock as a diorite, then if I will call it a diorite, I know that everyone in the world who are acquainted with this, they know that what type of rock I am describing. They know that I am describing, I am writing here or I am reporting a rock like diorite, means it is made up of plagioclase and your this pyroxene. That means your reduced a magmatic rock I am describing. So this is the thing that by which we are describing. Now, if you describing a rock in the field as a sandstone, the sandstone, that people know that yes, it is a siliclastic rock, but not only there, not only by a sandstone, you can characterize a sandstone. You have to go through some parameters or characteristic, and you should write it down there. Yes, so my sandstone is like this, and through which anyone can get any information, that is through that, only through the characteristics of that rock, one can know that what should be the energy condition, what should be the mineral matter there, what may be the possible provenance, what may be the depositional environment, and what may be the operational agencies or your air, water, or whatever, glacier, whatever it may be. So those things one maybe grabs from that your reporting or your information. So all these information should be there. So the first information that is most important, that is grain size. So grain size, textures, sedimentary textures are depending on these parameters: size, morphology, and fabric or arrangement of the siliclastic grains. These are the very important things, and you have to describe it to get a full idea of that rock. That is very much important. Otherwise, one cannot get everything from your description. So grain size, we know that a scale is there, Wentworth scale. So it is normally called Wentworth scale. So we know that just I was telling you that it is that I am describing a rock as sandstone. But a sandstone may be very coarse grain sandstone, medium grain sandstone, fine grain sandstone, very fine grain sandstone. So every sandstone that according to that your size scale, there are difference, and one may know that what should be the possible consequences of that. If I am describing a sandstone is a very coarse grain sandstone, then you must know that to deposit it, energy must be very high of the transportation agency. Otherwise, they cannot take it away from their provenance. It cannot be transported for a distance, and it cannot be deposited. So just by seeing the grain size, one can tell a lot. So that is the main thing. And if you can tell that yes, it's a very fine grain. So very fine grain means obviously, see, your place of deposition should be like that. That no disturbance, almost no disturbance is there, or very feeble energy levels is there. So these are the very important things, just to to describe a rock afterwards. So grain size, now I am coming to that and going to our scale. Here, there is a scale called Phi Scale also, that is minus log to the power 2, minus log 2d, but d is the grain size. So it extends from minus, I am So greater than 256, just you read it out, 256 to 64, 64 to 2, and this is all, it is the 1/8. So after that, so 2 by 1, 0.063. So boulder, cobble, pebble, sand, silt, mud, clay. Accordingly, naming is there. So boulder, cobble, pebble, it is within the conglomerate, we can name it. That is a boulder conglomerate, cobble or pebble conglomerate, like this. But for others, it is the sandstone, siltstone, mudstone, and claystone. And to describe it more conclusively and more easily, the scale is there, that is the Phi scale. So this is your Phi scale. This 256 is that -8, then -6, -2, -1 and 0. 0 is very close to this is here 1 millimeter size, that is difference between the coast to peripheral. So there is a mark over there. Beyond that, it is the gravel, rudite, boulder, pebble, this up to 2, less than 2, up to 1/16 millimeter, it is the sand, and from 1/16 to less than that, it is the mud. So accordingly, your Phi scale is there, -8 to 8. So it is the very important thing, and you have to, you need not remember all the time. Just you, after determining the size, you can go for the Phi unit in the table, and you can tell that what should be your Phi unit. It is going on. Some announcement is going on by my just beside my house along about your yes. So that is the thing. Okay. So next is the conglomerates. The first one, the very coarse grained ones. So this is the conglomerates, and we know that conglomerates are basically are of two types. Just to remind you, just to remember, you know that from Petition and those books we studied it, and we know that what is the name, what name should suggest. But just to remember, refresh your memory. It is the ortho-conglomerate is class supported, para-conglomerate is matrix supported. If it is a brachia, it comes within the conglomerates, but it should be angular, highly angular. We know false brachia. We know brachiated gauge. So those things are very angular classed. And class type. Now, within the conglomerate, what happened? Large rounded class or sub-rounded or angular class, whatever it may be, is there. But in their gap position, with these interspaces, there are matrix. So this is a totally, it is a matrix plus class. So depending on the class and matrix composition, the conglomerates are of different types, and they're named like that. If the class is of only one composition, that is you can take that it is quartz. So it is a monomic. If it is more than one composition, that is your quartz, feldspar, everything is there, it is polemic. But if class are poorly sorted of various types, number of types are there, not only 2 or 3, number of types are there and are very poorly sorted. They are called diamic. Possibly you know diamic. Diamictite is a rock used for the uh, for your glacial deposit. So it is called diamictite in that way. So everything is there in a hodgepodge situation and very poorly sorted. So, but basically they are conglomerates. And the next one is your this matrix. Matrix may be sand or mud. So, sand or mud dominated, this may be your matrix. And now, the very fine pore spaces which are not covered up by the matrix, they are binding by your cement. The cement are normally formed due to diagenesis, not in a loose condition. When the rock will be solidified, then only the cementing material will come, and they will be mainly of two composition, calcite and silt. So quartzose and carbonate, calcareous. So these two things should be the same. So basically, a conglomerate and brachia has been characterized by these. Just you see here now. This is a framework grain. Within the framework grain, this yellow part, they are the matrix. Matrix, it is called allogenic. Allogenic means it is formed with the formation of this framework grains. It is called allogenic. And then some triangular spaces over here, they are actually the cementing material it is orthogenic, and it is during the diagenetic process it has been formed, thus to binding the things. So crystalline cement, it is the crystalline cement, and this is called the matrix supported. Two types are there, and is grain supported. All of you are knowing matrix supported, when the within the matrix the classes are floating, and when they are touched with one another, they are grain support. So nothing new about that. So sandstone, now it is continuing. The class have modal grain size analysis. Sand grade class are there. We know from coarse to very fine, according to the Phi scale, according to the other scale, it is there. So, class, siliclastic rock class, the sands composition, sands grain size are like this. Siliclastic have class composed usually of mineralogy, quartz, feldspar, fine grained rock fragments, and lithics. It is actually called lithic fragments or lithics, and mud grade matrix, and then again this crystalline diagenetic cement. So for sandstone, after that conglomerate, the sandstone is coming. In sandstone, you know, different sizes, and accordingly name is also here. That is your this very fine grained sandstone, coarse grained sandstone, medium grained sandstone, like that. So we know it. So this is next one is the very important thing to describe a sandstone. It is very much important to describe its maturity. So maturity is a term which indicates a number of references that how the sandstone has been formed. So it is very much important. Maturity in that term, it is of two types. One is called textural maturity. Another is called mineralogical maturity. Textural maturity is a function of the sediment transport, as you are seeing here. You know that the degree of roundness or the amount of sorting of any in any sandstone, it will be increased if transport will be increased. So it's a function of transport, and with this the if a sandstone is more is having more degree of roundness or more amount of sorting, that means more well sorted. So that will be more texturally mature. And well sorted, very well rounded grains. So that's why they are matured. But matured in terms of what? Texture. But textural maturity does not mean that the rock is sandstone is mineralogically mature. So mineralogical maturity, you know, that if that will be more percentage of quartz grains are there, so the rock will be, the sandstone will be much more mineralogically mature. We know that in a sandstone normally quartz, feldspar and lithic fragments are there. So in that way, quartz should be much more in that sandstone, obviously more than 50% to give enough maturity of the mineralogical maturity for the sandstone. So mineralogically mature sandstone mostly quartz grain. If it is immature, mineralogically not mature, we know that means the opposite thing, that they will be enriched with your feldspar or lithic fragment. So those are the feldspar are those we know. So an arenite, if we are describing arenite, I am coming later. Arenite means more than 90% quartz. So naturally that will be texturally mature. But if that sandstone you are seeing under microscope, that yes, a sandstone is made up of almost 80 to 90% quartz grains, but simultaneously you are seeing that that sandstone is that sandstone grains are not well rounded, and the sandstone texture is also not well sorted. That means what you can tell from there, that your mineralogical maturity is high, but your textural maturity is not that much. So the rock has been formed, but it has not got transported much to get you the to give you the textural maturity. So this is very important. So and this maturity, mineralogical maturity, depending on the mineral stability. You know the Barnes reaction series, so from the magmatic rocks. So Barnes reaction series, it is just opposite the mineral stability. So mineral stability in Barnes reaction series, the list that is the latest forming mineral is your quartz, and in our mineralogical maturity, the first one should be your quartz, and the more mature, that is the more stable, maximum stable is quartz. After that, this, and you know, these two things we are getting, and in our normal your sandstones. So and some muscovites also may be there, but these are the that is the latest part of your buoyancy reaction series are giving you these, and all these ferromagnesian minerals. You know that they are biotite something obviously are there, but very less. But this is very important that plagioclase we are not getting in that way in sedimentary rock. Most of the time we are getting the potash feldspar or K feldspar, microcline, or this type of feldspars over there. So the ferromagnesian minerals will not present. So if that denotes the mineral stability. So you know it. Now going to the a plot that normally we are doing it. It is proportional in the that is your grain size in a phi unit in the x-axis, along the x-axis, and along the y-axis it is your proportion of detrital constituents. Thus suggest, just you see that in a sand silt interval, just in the sand grain size when it is a sand, monocrystalline quartz is giving you the highest, and feldspar is giving you the this green one feldspar, it is giving you the lowest. So monocrystalline quartz is having the high stability field. Rock fragment plus chart it is there. It is also increased at the first outset at the gravel part. It is much more, but when it is the sand and the finer sediments, it is less and less. But for the finer sediments, the clays and micas are available, so that will be much more. And accordingly, mineralogy also changes. That is your clays for the clays and micas. And polycrystalline quartz, you can see that it is not that much of stable, because you know polycrystalline quartz is made up of number of quartz grains, and they are fragile during the during their transport, and it may be like that one that the number of sandstone quartz grains may be separated out from the lump of that polycrystalline quartz. So that's why it is not that much stable, but monocrystalline quartz is giving you the highest thing. So increasing quartz is the increasing mineralogical maturity. Now coming to the other parameters that we have to describe a sandstone. Grain morphology. Three aspects of grain morphology are there. They are shape, sphericity, and roundness. These are the very important part. Yes, you know, all of you have read it in your earlier days. Just to refresh your memory, may have been forgotten due to certain work pressure. Just you and the perfect term you may have forgotten. So that is the thing. Otherwise, you know these things. The shape or that is your first one is shape. The shape or form of a grain is measured by various ratios of long, intermediate, and short axis. That is one. Different types of shapes are there. Bladed shape or bladed form. That is your oblate, prolate, spheroid. Like these all things are there. I am coming later. So this is the shape. Another is your sphericity. These two terms are very important. Sphericity is a measure how closely the grain shape approaches that of a sphere. So if a grain is there like this, so how much it is approaches a sphere within it. So this is very important. I am coming here after that. Just you see that what I have drawn there just now. So what is that? It is a the green one is a your grain, sand grain, and the maximum inscribed circle within the sand grain is the with the radius r. So this one. So this is the maximum inscribed circle. So these important thing gives you the, what is that? Gives you the sphericity. So it is giving you the sphericity. But roundness is something different, and it has got some 6 classes also there. Just you see over that how it has been calculated. Roundness, you see that high, it is angular and this is rounded. So angular, medium angular or medium rounded and rounded. So it is obviously, we know it is depending on the distance of transport. If distance of transport will be long and long, it will be more and more rounded. Obviously, by through abrasion, attrition, all these edges will be rounded. So it will be calculated roundness in a mathematical form. It will be calculated like that, that within this outside of this maximum inscribed circle, you are having some haphazard these angular spaces. Within the angular spaces, different circles of different radius will be fitted. The situation is like that. If the small circles, it is having R1, R2, R3, R4, R5 like this, then R1 by R plus R2 by R plus R3 by R plus R4 by R plus R5 by R. So all these things will be summed up and then divided by 5. It will give you the perfect roundness of that grain mathematically. And it is very important, if anyone just you see angular, rounded, sub-rounded are the qualitative term. If anyone is working with some particular domain, that yes, roundness, their mathematical application should be there for some your this calculus or integral calculus should be a part of that your work. Then you have to determine the perfect roundness mathematically of the grains, and that can be measured through your this petrography also, because taking an image of that, after taking an image of that sandstone, the grains will be there, and then you can inscribe circle and you can measure the things. So that is another image processing that can be done through that. So roundness, just you see the grain shape, very angular, a chart is there, subangular, sub-rounded, rounded, well-rounded. What we will do when we will describe a rock in our drilling time, or in our this different exposure, we are writing like this: very angular, subangular, well-rounded, sub-rounded, like this. So it is according to a chart. Roundness chart is there, and that's the way of describing about the form or shape. The form or shape is like that. That taboo, just you see that C by B. You can see, I think that is the C by B. That is your small by intermediate axis here, and your intermediate by long axis is here. So if we plot 4 quadrants are there, this should be tabular, equant, roulette, and bladed. They are very important to describe these things when anyone is doing a project, or he or she will be doing with the stress strain aspect of any sedimentary terrain. It is very important. Just keep it in your mind that to measure the strain due to a particular stress of a rock, of a sedimentary rock or a sandstone, you have to measure this, because you have to measure that whether after giving a certain stress, your bladed figure is going to your roulette figure or not. So that is very important, that your shape will be changed. And you know that a circle that is a well-rounded, maybe it will be changed in an elliptical fashion. So that is very important in that domain. And that's why it has been studied in detail. So grain shape. Now the last one is your grain
Sir,
fabric according to this.
sir,
What is,
sir.
hello?
Excuse me, sir.
Hello?
The last slide, sir. Last slide में hello.
Hello.
Last slide में sir में sir ये जो है what is indicate A and B and C, that is the length of ये sir A, B, C.
Huh? Plot,
What
that is
is
the
A
plot
is
of
the
the
base? A
A,
is the
B,
base
and
of
C are the axes. Are the
axis.
axes.
Axis.
Okay, axis. C is your. So
Height.
I am telling you. These are the three axes.
Yes, sir.
Okay, these are the three axes. It is your
Yes.
A, it is your B, and it is your C. According to your three-dimensional figure, A
Yes.
is this is
A
your
axis.
short, intermediate, and long axis. Okay,
Okay, sir. Thank you, sir.
got it?
Yes, sir. Thank you, sir.
Okay. These are the A, B, and C are the three axes of any three-dimensional figure. Okay. Now, going to the grain fabric. Grain fabric is giving him how the grain is packed. It is loose or it is well packed, or what are the grain to grain contact. Those are very, very important. Now, grain packing is a function of the size and shape of the grain and post-depositional physical and chemical processes that bring about compaction of the sediment. Just you see over here, grain to grain contact, it is called actually the grain packing. These are the sutured grains. One sand grain is the contact is sutured like this, and this is sutured. What is this? This is concave convex contact. So this is a point contact. This one is a point contact, just a point with that. Long contact, a long part is in a contact. Floating grains, no contact within this. Concavo convex. It is also concavo convex. It is also concavo convex. This one, concavo convex, and you may call it as a convexo concave also, depending on the grain in which it is including. And if this is the situation, you can take care that a number of the type of contact of grains are there, and grain orientation is also a function. Grain orientation, it is also a very good function of the physical processes, condition of operating at the time of deposition. Just I told you that if some shear I will apply during the deposition of a sandstone, then what will happen? They will be a linearly directed. There will be a fashion, there will be a fabric along which the grain orientation should be there. That means there may be some grain orientation. If the grains are oriented in that manner, then that is definitely a function of some physical processes. So that is also very important to note under the microscope, that whether what is your grain fabric, it is having a orientation or it is not having. And we know when you are studying a schistose rock or a gneiss rock, we know that there is a linear fabric is there, a planar fabric is there. That is actually called the grain fabric. So if it is in our sandstone also, it is like that. And if we are going to through this, it is have different connotation. Sutured gain like this. What does it denote? This denoted different types of things. That may be post-depositional changes, that may be some chemical processes operated on it. Now, what is I don't know. I have to study the other parameters also, other textural criteria of that particular rock, and then you will come to conclusion. But just seeing it, one can tell that what should be there. It may be like that, that it is a your the rock may be your this quartz reef. It has come from a quartz reef, so that the one quartz grain is associated, is in contact with the other. It is called the fish scaly fashion, just like the scale of the fish. So it is from the quartz. It is from the quartz, and it is from your this quartz reef sandstone. And if it is not there, then another criteria may be there, that it may be pressure solution. That means due to some pressure, directionally activated pressure, some part of the contact is going to the solution and it is creating some zigzag contact. So sutured contact, it may be like that. So those things are there just to study over that. And I am coming over here, just you see that just I have told you pressure solution quartz grains. What happened here? two things is there. It is the write-up is sort of a small one. Whatever it may be, what I want to show it here that all these three things now are almost same. The right part, it is the overgrowth, overgrowth on grains, and it is the pressure solution system. What happened? Pressure solution system. Just you see that there is a some three it is also called 3-point junction. Can you see here this one and this one, this one, this one. So it is actually the 3-point junction. So 3-point junction will form everywhere. 3-point junction will form after the pressure solution, and after the pressure solution means a pressure is activated on that, and now the pressure has been released and we are getting it. And here how I am telling you. And another thing is, it is very important, very important. And another thing here, you can just you see first, just you see that each and every quartz grain has a overgrowth over there. So each and every this part overgrowth, and this is also a overgrowth. So all these things are overgrowth. So a quartz grain was there, a quartz grain initially was there, and above that quartz grain, following that boundary, some overgrowths are forming. That in sediment supply should be there. With this, it is following the morphological behavior of the internal, the internal sandstone sand grain. So it is obviously it is orthogenic, and it is forming due to diagenetic process. But here what happened? Possibly you know this thing, that is the in the metamorphic rock or a stressed rock, it is called 3-point junction is called the recrystallized texture. I think you know these things, that there is a 3-point junction everywhere in a proper recrystallized rock. 3-point junction. How the 3-point junction are like that, that they are 120-degree apart from each other, because this fashion, this crystalline structure is having the least energy, and all the energized, that is the stressed particles, are trying in nature to go to the stabilized one. So the most stabilized one is your this 3-point junctions, or is 120-degree apart junctions in a stressed metamorphosed rock everywhere. Here also I am calling I am taking the of a pressure solution. Then there must some pressure. So a rock was there. If I created some pressure over there, so this pressure is creating some directional pressure within this, and the grains which were there earlier, they are pressure solution will be created in the junction of these two grains, and they have been liquefied. After liquefaction, again, when pressure will be released after some time, then they will be stable, and when they will be stable, again they will be recrystallized after that, and they will get the shape of this three having this 120-degree apart system. So that is very important. Just looking after under microscope, you can categorize these things. And so I think it is clear to you, everybody. So now coming to the classic,
सर
any question, please?
हाँ सर, मैं बोल रहा हूँ कि क्वार्ट्ज ओवरग्रोथ है, दैट इज मेन कॉज ऑफ ड्यू टू प्रेशर.
Which one? Which one?
Overgrowth of quartz is mainly due to the cause of ये pressure.
Just in the right side, at the outside, I told that
Main cause
these are due to
only one
overgrowth.
factor, other factor sir. Overgrowth जो quartz overgrowth है, उसका
Yeah.
main factor है pressure, और any other factor sir?
No, it is not under the pressure. It is due to these things are due to the substance, that the rock that has been that is going in the diagenetic process. During diagenetic process, the solutions. Huh? It actually, when it is rounded or like this, and we are having the overgrowth over this, we are not we don't consider about the pressure solution. we consider that it is just an overgrowth. It is overgrowth due to diagenetic process. But if it is like this, with no overgrowth and some sutured grain will be there, and with these three point junctions over there, we will consider the pressure solution. These are the differences. I am showing you the differences. This pressure solution and overgrowth are not the same thing. Okay,
Achha. Mhm.
got it?
Yes, sir. Yes, sir.
It is overgrowth is due to the normal process. That's
Normal
why it is
process.
overgrowth. Orthogenic
Mhm.
process. Okay,
Mhm.
orthogenic process due to diagenesis. But it is
Mhm.
not due
Yes.
to diagenesis. It is due to
Mhm. Yes.
some directional pressure.
That will. Mhm. Yes, sir.
Right?
Yes, sir.
Okay. Then. Very good question. Then coming to the next, you know these things. I should not go to detail. Just you see and reconcile yourself. That classification of igneous rock, classification of siliclastic rock, Crompton 1962 Petition, and we are following these things, this Petition classification. And the main thing, what I should tell, that the three vertices are gravel, mud and sand. So they are taking gravel, mud and sand. That means the lithic fragment, the matrix and the lithic fragment, matrix and cement. Everything they are taking into consideration. And the corresponding figures have been changed. That is, it is the modification, you know. So it will be modified later also, and we should consider the latest updation, that what is going on in the international journals, or what are the actual latest classification scheme. So these are the earlier ones. It is going on. Just to just how to this is how this has been measured. You know that how many gravels are there or how many sand grains are there. So how it will be measured? It will be measured through your this point counting method. So this is the point counting method, you know. So this is the your these grids are there, point counting, normal point counting method. And for each and every square, feldspar, rock fragment or matrix, for each and every parameter, we are ticking our point counter, and we are getting that how many numbers are coming for each and every parameters for quartz, feldspar, rock fragments, like that. Then we will recalculate it with respect to 100, and then we will plot it. So normally 250, 32 to 300 grains will accurately hit the proportion of each component. This is very important. And nowadays, what we can do, we can take a photograph also over that, and we can take obviously using the image processing softwares. We can do that. What are there? What components are there, and what are their actual volumetric proportion, that can be made out to the image analysis diagram. So this is the dot scheme by point counter. You know this. Now classification of silicic cluster is continuing. So to classify, now two terms are coming: arenites, grey water, on the basis of the specific composition. So 100% this is quartz, feldspar and rock fragment. Just I told you, that is a triangular diagram. Now, if the proportion of matrix is less than 15%, we use the plot, that is the dots diagram, for classification of the arenites. The classification is based on major component of most of the sandstone. Just go to the diagram. That will be easier. Classifying sandstone, mineralogy. So, folks, classification 1968. All of you are knowing it. So, greater than 95% quartz arenite. If it is less, up to 75, sub lith arenite. This one. Why? Because this is the lithic fragments. This is the rock fragments. R is rock, lithic fragment. So this part is lith arenite. It is lith arenite. It is sublith arenite. It is felspathic lith arenite. Accordingly, it is arkose. Feldspar is much more. Arkose up to 75%, and then it is the subarcose, it is litharcose, like that. So you know the classification scheme. This is according to your 1968 Fox classification. Now, when it will be arkose, the total this red part is arkose. greater than 25% feldspar is arcosic composition, and obviously if a rock is greater than 25%, having greater than 25% feldspar, it is mineralogically immature. You can see a arcose over here, so we can tell that the rock is mineralogically immature and it is an arcosic rock. So we can determine through point counter or through image analysis that what is the volumetric or modal proportion of this quartz, feldspar and lith fragments or rock fragments over there, and we can plot it over here, and you can see that our plots should come over some places like that. That is, it is the R codes. So that is the thing how we are plotting it. Now going to that one, that is a clastic, the siliclastic rock, what a sandstone, 25% of our secondary stratigraphic record is the sandstone, and accordingly we name there that is a quartz arenite, arcosic arenite, just you see earlier. So this is your arenite. Within this arenite also some classification has been made to describe a rock more intelligently, to describe a rock more meticulously. So this is quartz arenite, arcosic arenite, lith arenite, and if the proportion of matrix or mud is greater than 15%, then it is a wake coming over there. Just you see the classification of sandstone after Petitjean 1975. It is in vogue. It is going on. So here the quartz arenite, sandstone, arcosic arenite, leach arenite, everything in sandstone is there. So if we can identify a rock under microscope that it is a sandstone, we go for that those your image analysis or your modal analysis. We plot over here, and directly we will see that in what domain, what region it is falling, and we can name it from there. So this is lith arenite. So this is a arcosic arenite. This is quartz arenite, and these are the up to this. This is the arenite. Just you see, this is the matrix regime. Here, this is the matrix regime, percentage of matrix increasing towards this side. If it is increasing, if your matrix is greater than, if it is your 50%, 15% level, if it is 15% level, then this level, then it is called the wake. Then it is lithic wake, not arenite, not arcos. Arcosic wake, lithic grey wake, which is quartz wake terms is coming. So now, if it is more than that, 75% level, it is totally mudstone. It is not a wake. So you can see from this diagram that the wake, that the most of the area that is your interspaces are more than 15% of your mud or clay minerals. You can call it a clay also. So if it is like that, then you are taking it as a wake. So this is the basic difference. Matrix different. More than matrix 15% is your wake. Less than 15% that is your arenite. So this is the important thing. Now Petitjean classification. It is written over here. Matrix 4 less than 15% arenite. Matrix is greater than 15% is wake. So wake is tend to be a darker color. So already described. Now based on color, one thing then again come, it is color. When we are describing a rock in the field, we are studying the color first. What is the, it is a light color, it is a gray, it is a dark gray, or it is a white or light gray, like that. So these things are very important. The based on the color, quartz arenite, obviously pure quartz, it is a light color. Arcosic feldspar is some light color. These lower two are dark color. Just you see, lithic sandstone, rock fragment rich. A grey wake, it is also rock fragment. It is also dark color, but it is matrix rich. So when we are describing a dark colored sandstone, may be very important for that. That what dark mineral we are seeing, they are lithic fragments. They are certain minerals, or the most of the dark coloration is coming through the matrix. So this is very important. Accordingly, the name may be changed. It may be sandstone, it may be wake. So based on the color should be written over there. And next one is your grain size distribution. Very important thing, that sorting. Sorting is that is we know, we already discussed earlier that that is your textural maturity. Textural maturity will be increased if your sorting will be increased. So sorting is nothing but that. From the figure, it is very clear. You can remember these things, no problem. That is a very well sorted. Just you see the upper left one diagram. This one. Just seeing it, you can tell. Yes, it is very well sorted. That means almost all the grains over here are almost shapes are in an average shape is there. It is not like that one is very small, one is very large like that. So it is called very well sorted. If the sorting is like that, that okay, some grains are there that those are large grains, other grains are there, they are small grains. Then it may be like that, it is well sorted. And if there is another grain size is there within these two, they are not that much sorted. It is called moderate sorted. And if there is a hodgepodge over there, that is a very large size to very small size, everything is accommodated within this poorly sorted. And it is, if it is further increased, that is very poorly sorted. So you can see that from very well sorted to very poorly sorted, and you can also see that this is a qualitative curve just based on the seeing under the microscope. I may tell that a rock is poorly sorted. You may tell, seeing the same rock, it is very poorly sorted. It is just after us who are seeing it, and in what angle, in what part of that rock. That is also very important. So these things are really very important. And to avoid these problems, to avoid these confusions, here comes some parameters. It is the numerical figures are there. How it can be determined, I will tell you. But if the your value now particularly following a particular process, if I tell you that yes, my value is zero point 0.4 for this rock, and you have studied the same rock, you are telling that no, my value is 0.48. Now coming over here, all we are talking about 0.35 to 0.5. So it will be also. So here lies the significance that why these numerical parameters will be invoked. So we have to consider this one. Otherwise, in the field, just seeing a rock under microscope, we can tell that whether it will be very well sorted, moderately sorted like this. But when you are doing some statistical analysis over there, some grain size distribution or grain size analysis, you have to depend on the mathematical value, not only the just textural seeing after the under the microscope. So I think you get it. Next one, this is a grain size parameter. It is going on. This is the statistical parameters. So statistical parameters, there are four parameters which are very important to describe a texture of a sedimentary rock. These are mean, sorting, skewness, and kurtosis. So these things we will now describe. All these things are based on your statistical parameters. And we know that grain size analysis from our very undergraduate days, those we have those who have studied sedimentary petrology, sedimentary petrography in more detail, they know that to classify a particular sandstone or a sedimentary rock, you have to analyze the grain size parameters and through the statistical method. So here, if we plot according the phi interval that you know now, phi scale, that is our what we should do, we should crush the rock, we should powder the rock, then according to different mesh, that is panning should be done, and we will take the fraction of those panned material, that in which mesh factor or which pore factor, that how much more volume has come out. So those are the percentage, volume percentage, and we will plot like that. Now we are seeing here that for 0 to -1 level, that is your sandstone level, medium to coarse grain sandstone, this is the maximum histogram is coming over there. And after that, less, and less. So there is a median value. So there is a maximum over there. After that, it's like that. Now it is the popular histogram. And if we will not give our presentation like this, we may give it like your frequency card. No, it is the same like that, taking the midpoint of these, everything, and these things is giving you the this card. Okay, so the frequency curve of the sample is like this. Then the cumulative curve. Cumulative is like that just adding up one after another. So it is not up to 100 level. So when we calculated it 100 level, then from point 3 minus 3 is coming over here, minus 25 is coming over here, minus 1 is coming over here, then again 0 is coming over here. That is your 60. That is your total cumulative percentage, 60 percentile. So there are this is actually called the percentile value, and 25 percentile, 75 percentile, they are 50 percentile, they have different meanings. So this is the card, it is called the cumulative frequency card. You know these things, I know. Still I am describing. So the old fashioned way, modern way, just okay. So we have to study these things, and there are these are the methods of graphical representation. Actually, we are doing the mathematics, the rigorous statistics, and from the statistics, we are presenting ourselves through these cards. So, graphical parameters are there and mathematical parameters are there. One may prefer graphical parameter, one may prefer mathematical parameter, but both the things are same. But just to describe the things, just to represent the things, for our sake, we know that the graphical parameters are best to interpret that what types of grain size parameters are here. So we will follow the graphical parameters, but the basics are coming from the rigorous statistical analysis by different methods, standard deviation method or like that, kriging method, everything is there. So just you see, grain size parameters for graphical method, graphic mean Phi 16. What is Phi 16? This is 15, here 16. Just you see that here is your phi, that is your 16 value will come. What here? So what is that? Now phi 16, phi 50, phi 84 divided by 3. This is actually the graphic mean. Standard deviation, the formulas are there, need not going to those detail, but we have also calculated in our days that by hand that what should be the skewness, kurtosis by this graphical method, and afterwards you have to you may compare with the graphical representation data that the statistical analysis are okay or not. So this is very important. But from this only the graphical parameters are there. Just you see moment measurement, mathematical method. Moment measurement. By moment measurement, there are four moment. First moment, it is in the mathematical way. It is called the first moment, second moment, third moment, and fourth moment. First moment, it is the mean size. Second moment, it is your standard deviation. Third moment is skewness, and fourth moment is kurtosis. One may also do like that. Just a minute, a phone call is coming. Just a minute. Hello? হ্যাঁ, পার্থদা আমি একটু পরে কথা বলবো, আমি একটা ওই অফিসের একটা মিটিং এ আছি। হ্যাঁ, ওই অনলাইন, আমি একটু পরে হ্যাঁ, 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 হ্যাঁ। ওইখান থেকে ওই যেখানে একদম একদম ওইটাতেই, ওই ওইটাতেই। হ্যাঁ, ঠিক আছে, আমি তোমাকে তাও পাঠিয়ে দিচ্ছি পরে। ঠিক আছে, ঠিক আছে। Okay, so then the mathematical methods are like that. So there are different moment analysis, and we did not do it. Just don't scared about that. So we do not do it. What we will do, it is this statistical. It is the that is your the just uh, just a minute. May I take a 2 minutes break? May I take? Hello.
Yes, sir.
Yes, sir, please, sir.
Hello, just 2 minute break because I have to take one medicine. What I have forgotten. Just I am taking and I am coming. Okay, just you feel over that. I am coming. Okay, so different procedures are there to represent your data. The data you have accumulated from your study, you may show it by univariate histograms, by bivariate histograms, frequency polygon or frequency curve, pie chart, bar graph, or this mean median mode like that. It may be that means the frequency distribution curve, or in any way you can represent your data. Now, which curve are what are the meaning of the different curves? That is very important. That I am coming over here. So now, excellent. Okay. So the first one, it is the main curve, that is your this bell curve. The natural distribution of any substance should be like this. There is a high in the middle part, and then the confidence level will be low and low, and then we are getting this bell type of curve. So this bell type of curve is a normal statistical distribution curve, or for your any statistical data, natural statistical distribution data. And we know that few slides back I told you that some quartile is there. It is called quartile at 25% level, at 50% level, at 75% level. So three quartiles are there. It is called Q1, Q2, and Q3. Now, difference between third and first quartile is obviously Q3 minus Q1. Spread in the that means here it should be Q2, here it is Q1, and it is your Q3 at 75%. So it is 50% level, it is 25% level, it is your 75% level. So Q3 minus Q1 is the difference between the interquartile range. It is also important for some reason, not affected by, and spread in the middle part, that is the bell curve, main bell curve is there 50% level. So at 25% and 75% level, the curves are diminishing, and at the 50% level it is high. So this is the main dispersion pattern of a bell curve. Now, okay, it is already I have described this, the textural and maturity. I don't know how the is coming. Okay, leave it. What is the very important part? That is your just coming over here. Mean, median, modes. These things. That is this last figure. I will describe it later. So, just I have kept it here for how it will be. How it will look like. That, and what is the meaning of that? I am coming afterwards. So the first one is mean. We know the parameters mean, median, mode, and with that, all these things are your associated with your skewness, kurtosis, like this. How they are determined and what are their significance. So here now the mean we know sigma I by n. So this is the mean. If mean is there, the mean reflects the overall average size of the sediment. Now what are the influencing factor? Influencing factor is the source of supply and environmental deposition. So depositional significance of mean is very important. When we are getting a mean, we should think about that mean is that much, overall average size is this. The overall average size is coarse, a coarse grain material. If it is the coarse sandstone or very coarse sandstone, that is the overall average. So we should think about that what should be the source of supply. Source of supply must be very near. Source of supply based on the your mineralogy. What is the source of supply that may be done? So and environmental deposition that is nearer to the provenance, that may be pointed out from there. So the mean average, and if it is overall average is size is very small, if it is a very fine grain, then the connotation are different. So this is the thing. It is influenced by parameter like obviously velocity of transporting agent. Why velocity? A very high velocity current will give you a very high overall average size. If it is very low, so the velocity will be low. Now the shape, specific gravity, composition, durability, resisting nature of the sediments, all these things are associated with the average value, average size of the mean size of the sediment. The grain size will be larger if the amount of the imparting energy of the sediment is greater, and it is low if it is less. We know these things. So the tremendous depositional significance is there. So just see the mean value, you can tell a number of things about the velocity, about the energy of the current, and about the depositional environment also. So this is the mean. Next is standard deviation. Standard deviation, it is actually it is dependent on the size of the sediments and degree of sorting. It is actually denoting the degree of sorting of the sediment, and it is expressed by the standard deviation. It is a measure that to know the processes or absence of coarse and fine grain fraction. You know that we just a few minutes back we told about that your what is the sorting? Very poorly sorted, moderately sorted, like that. So if sorting is like that, we know that the admixture of the sediment, if there are two modes are there may be two modes, a very large size of grain and a medium size of grain. So there are two modes. If there are two modes, so absence and presence of this coarse and fine grain sandstone fraction is very important to know. That is the degree of turbulence, velocity of transporting agent, hydrodynamic property, everything. That what type of sediments we are getting, and nature of sediment supplied to the depositional, nature of sediment also supplied to the depositional environment, it is very important. So well sorted to moderately sorted nature are probably due to addition of sediments of different grains from reworking of these beach ridges or prevalence of strong wave convergence. That means, which is very important, that if it is well to very well sorted, we know that it is the winding of the grains. It is again winding up and it is rolling back. Again, it is coming forward. So back and forth motion of the grains according to the strong wave or some in the beach river, the beach environment like that. So they are very well sorted. So there is a popular distribution of one mode distribution that is only very well sorted. If it is not like that, if it is not well sorted, if it is ill sorted, or if it is poorly sorted, that means number of different modes of admixtures are there. Those denotes number of different environments may be associated with this, and velocity of the transporting agency is fluctuating. One, maybe it is hydrodynamic property, may be fluctuating. So all these things may be done, interpreted from there. Now coming to the skewness. Skewness is the depositional significance is like that. Skewness is nothing but the asymmetry of the particle distribution. So before going to that depositional significance, I want to describe it from this. Just you see, if it is here, you can see it from here, the last figure. Just please see it. That first one is negatively skewed, middle one is symmetric, last one is blue one, it is a positively skewed. What happened? Symmetric means no skewed at all. That means no your larger substance, larger sediments are there, larger grain size are there, nor smaller grain size are there. The bell curve is almost symmetrical. Now we know that what are these? After this median value, this is the regime of large grain size, and this is the regime of small grain size, because grain size is increasing in that way. So if the grain size are larger, the mode of the grain size are larger, and the your curve is more towards the larger grain size, it is negatively skewed. If the grain size is smaller and your curve is towards the smaller size, it is called the positively skewed. And when it is not there, any skewness is not there, it is called the median symmetric presentation. So you are, and another thing, you are seeing here one thing. This is just clear it. It is very much important. That's why I am telling the median. It is the median 50 percentile. It is your mean. It is your mode. If it is like that, the mode is maximum over here. You know that is a negatively skewed means coarse grain sediment is there. If median mode is greater than your mean, then it will be negatively skewed. If mode is in the last figure, if mode is less than your mean, then it is your positively skewed. So going to there, just you see skewness. Before that, it should be there. Symmetrical distribution, approximately equal numbers of observations are made above and below the middle, so all are same. Skewed distribution, one side is more spread than the other, and it has a tail. Direction of skewness, now you know, you have seen the figure, positive or negative, right or left. Rightly skewed means obviously it is negatively skewed. Rightly skewed means that is your grain size is larger, negatively skewed. Left side, left way skewed means it is positively skewed. So side with fewer scores, okay. If median greater than mode, skewness positive, just you have seen. Median mean less than mode, skewness negative. Mean is equal to mode, skewness is 0. So if anyone is doing the mathematical procedure, going through the mathematical procedure, and he is seeing that his mean is almost equal to mode, then the skewness is 0. So it is very well symmetrical, very well symmetrically distributed. It is not skewed. If mean greater than mode, it is positively. If mean get less than mode, negatively. Possibly you have got it. Now its significance. Skewness measures the asymmetry of particle distributions. Now it is clear to all, I think, that it also shows that how close grain size distribution, Gaussian probability curve. This is the Gaussian probability curve. Advances the Gaussian probability curve. It is the Bell curve. The prevalence of negative skewness. What does it denote? Imply high energy and winnowing action, whereas positive skewness, where that is the mean is less than the mode. What happened? Low energy condition with accumulation of fine sediment. Just seeing the curve, you can tell the energy condition. So that is very, very important in that respect. Nature of sediments implies that occurrence of high to low energy condition with mixing of coarse to fine grained sediments and also indicate mixing energy environment. Association of coarse with fine sediments is due to washing and backwashing of wave current. Then if the curve is like that, if the curve is like that, what does it mean? That means, yes, negatively, positively skewness is there. That is, your finer grains are much more, but there is a strong distribution in the positive side, that is negative side also. That means your higher, larger grain size are also associated with this with the negative one, if not symmetrical. So if it is, I want to mean that if it is like that, then there is a mixing of the coarse and fine. If it is a mixing of coarse and fine, then the situation, energy condition, it is also different like that. So you can easily delineate the deposition of significance. Now you can see symmetrically just bar diagram. It is a bar diagram. Bar diagram, it is a symmetrically skewed. You can see negatively skewness. You can see positive, negative skewness, and it is a positive skewness. So the your this very important, that is skewed right and skewed left, and almost no skewedness at all. So after that, it is coming the kurtosis. Now, that is one another parameter which we have to describe statistically for the grain structure size analysis of the for the sedimentary texture. The kurtosis is the qualitative measure of parts of the sediments already sorted elsewhere in high energy environment. What does it mean? It means that later transported and modified by another type of environment. Go to the figure first, and then you can, yes, this one. Just you see, skewness class. Skewness, that is the sorting. You see that mathematical values are also here, this skewness. So it is positively, negatively skewed is here. Accordingly, kurtosis value, kg class, this is also like this. And now we are dealing about the kurtosis. It is the skewness earlier one. Kurtosis, it is just telling you that the pickedness. Pickedness means how we are having this bell curve. We may have this bell curve like this. We may have this bell curve like this. We may have this bell curve like this. And we may have a bell curve like this. So if the bell curves, these curves are like this, statistical distribution are like this, they are having different connotations. If it is like this, that is the normal distribution, the green one you can say, this one, normal distribution. It is called mesocartic, and the value is, according to the mathematics, statistics, 0.90 to 1.11. That means the your average is 1 almost. So if it is 1, then it is your mesocartic. If the value is less than 1, that means it is less than 1 means this one, this green one. I am telling, this is the green one, this one, a little blue one. So it is less than the pickedness. It is called the pickedness, the peak value. Peak value is less over here in the blue. So it is called the platycartic, almost a plate-like substance. That is the, here we are getting a plate-like behavior, flat behavior. It is called platy. But if the pickedness is much more high, higher value, it is called the leptocartic. So three things are there: leptocartic, mesocartic, and platycartic. Accordingly, you can classify like this also, very platycartic. That means it will be, I can tell you, it is like this, very platycartic. Then platycartic, then mesocartic, then leptocartic, then hairy leptocartic. Hairy leptocartic means within this distribution level, I cannot increase the distribution level. So it may be like this, hairy leptocartic, extremely leptocartic. So all these things are different connotation, their significance. What are those? These are actually very important for the recycled sediments. If a sedimentary rock is a recycled sedimentary rock, then the signatures must be there when we will do this analysis according to your kurtosis, that is your leptokurtic, mesokurtic and platykurtic. It will show you that how much it is. Just you see, here the graphic kurtosis, graphic value, later transported and then modified by another type. Just you read here in between line. Very important. Later transported and modified by another type of environment. So once it was formed, again transported and again by another environment. So these things can only verified through this kurtosis diagram. And again, kurtosis is the ratio between the sorting of either extremes to the central portion distribution. You have seen the pickedness. If the central portion is best sorted, then the extremes, then the frequency curve is said to be excessively peaked. You have just seen excessively pickedness or excessively leptokurtic. If it is not, if the extremes are better sorted, here extreme means this one. Just you tell, these are the extremes and these are the central part. Okay, if extremes are much well sorted, then it is you can tell that that is mean and median that is not preserved like that. So if there is a single time of distribution, sedimentation and transportation, there should be one single type of distribution of median and mode. If it is not like that, it may be like that, that we are getting everywhere where the recycle is there, we are getting like this. Like this one. That means number of pickedness. Number of pickedness means each and every kurtosis value is giving you a number of sedimentary cycles. Number 1, number 2, number 3, number 4. So at least 4 sedimentary cycles have been witnessed by this sedimentary rock that we are seeing. Now what are those? We have to fix it up from the other things. But it is very sure that we are seeing at a recycled sedimentary rock. Clear to all, I think. So this is very important. What is this rock? You can see it. It is a very very poorly sorted rock. A figure I have given, diagram I have given here. Very poorly sorted rock. So everything is just jumbled up here. And you can, if you have distribution pattern, if you show, if we can show you the distribution pattern must be like this, must be like this. So some pattern will come. What actual pattern? It is your duty to determine it through the grain size analysis. So if you perfectly do it, you will get that sedimentation cycle all over. So this is very important. But here also it is there, but not that much. Not that much. You can see that if, and another thing is very much important here. A faint linear pattern is there. Here also. Here also. Here also. So this sedimentary unit must have gone some differential, some stress pattern. So this is very important from there, and it is also a history which affects its tectonic history, its sedimentary history also. So taking all together this, you can land up in such a position that from which and from how the sedimentary unit has been formed, it will be clear to you, and you can tell a lot about that. You will get this statistical parameters. So okay, so this is done, and now I am coming to deposition. Just you see what havoc we can do by these. Just bivariant plots. We have told the sedimentary and the depositional significance, everything from the each and every individual parameters, that is statistical parameters of grain size analysis. Now, if we club together them, And we have gone for the bivariant analysis, taking any two of these parameters, it will do a havoc for it. So that's why I am telling these things. The bivariate plots of between different textural parameters throw light on the information regarding depositional environment, sedimentation, different things, and it is much more giving you the along with your the singular value of this skewness kurtosis, it is giving you a conclusive remark on that. Just you see, I am showing you some plots. Just you see, it is the omni speaking. That means it need not be told anything about that. So you can see that it is the plot mean size versus standard deviation. It is a plot from one of my paper, obviously. So I plotted these things. Just you see, a very good indicator of this difference between river and beach. So which sediment will be there from river and beach? It will be the plot is against mean size and standard deviation. It is written here. Mean size and standard deviation. Here mean size and median size. It is also there, and earlier works also there about that. That is the I have given the reference also. Anil Cherian in 2003 have done it, and I just followed him. One, this is just you see Cherian skewness versus median. You will get beach and river. Now, wave beach and river, Daniel, kurtosis and median. When you are taking the condition of this kurtosis, why? Why? Because if kurtosis is there, you will get the recycle part. So if it is river over the or wave is there, once it is going there, another it is coming. Again going there, again coming there. So that may be the due to that this wave. So everything will be taken together. It is kurtosis versus median. Skewness versus standard deviation. Beach and wave, river is a Rajamanikam, Mohan and Rajamanikam 2000, Anil Cherian, both of them had utilized that, and there is a line of there. Beach, wave, foreshore, strand line, river. Just you can plot it and you can get a very good result. And I am sure, I am telling you very confidently that all of your these parameters that you have drawn from your statistical analysis will match with your petrography also very good. So when I am telling that yes, my these data are coming in the foreshore level, I have seen that it is tremendous mineralogically mature. That means obviously should be in the foreshore level. So quartz is very high, about 80% over there. But here in the river part, it is not like that. And this is the very important thing. And another thing is coming out from here that foreshore is there, beach or wave is also here. Why the data is concentrating in the foreshore? Because in the beach, it is the upper tide level part, and in the foreshore, it is the lower tide level part. So my data is concentrating in the lower tide level part, below the floodplain level. So that is the connotation that I am taking from here. So here also skewness by mean by standard deviation. You can see dune and beach. You can perfectly corroborate it with this. I have taken some sand from the dune, and it is falling over here as marked over here in the dune. It's very good, and it is again Friedman. So these Friedman, Moila, Weser, 1968, everything is there. They are doing like that. So I have just plotted. So mean versus standard deviation. You can see now CM diagram, CM passager diagram. Passager means it is the C means first quartile, M the x-axis is M median, and C is the first quartile median. This is giving you the yes, this is your suspension load, and this is your rolling load. Once it is going up, the rolling load is increasing. That is your substance will be rolled. That means very high energy level. Here is the medium energy level. If your data concentrating here, it is totally suspended load. That means very low energy level. So this is the thing, transportation, processor and depositional agents. So that can be marked out from here. So up to this, those things are completed. After that, I will not tell this in detail, and I have not kept it also in detail because it will be taken by later by another lecture. So sedimentary structure, just I have taken it here For that each and every this procedure, this process, wave, beach, dune, everything, they have their signatures on the sedimentary structures. So the sedimentary structures from microform to mesoform to macroform, ripple, dunes, bars are there. So I am not going to any detail, just to show you, and then I will go to another aspect, the last aspect. So lamini bed, very small, less than 10 millimeter lamini. It is greater than that, that is bed. And normal grading, it is the normal grading, that is a fining upward sequence. The reverse grading, portioning upward sequence, that is the fining up of a series of beds. That is a bed. It is within a bed. It is the non-graded bedding, and it is not within a particular bed. The different beds are there, and it is the fluvial in the fluvial cycle. It is like that, and it is your, sorry, just talking bit, in the delta, upper delta, it's such sequence. It is the delta front. It should be like your portioning upward. So normal grading, finding upward, portioning upward there. It will be delta earlier, later. Now cross stratification, two things are there: cross lamination and cross stratification based on their size. So small scale or large scale, like that. And planar cross stratification, trap cross stratification, just I am going to one figure, and then I will leave from here to other parts. Just you see, it is a small scale, large scale cross stratification. All of you are knowing. Sediment input by sediment output is a very important phenomena. If sediment input is very greater than sediment output, then this cross stratification only preserves, otherwise not. And if this is much more, then we are landing upon the climbing ripple situation. That is the more and more sediment supply with more and more energy, and it will climbing upwards. So it will be climbing ripple. So this factor is very much important. As I have told, this planar cross stratification and trap cross stratification. So that this is the trap cross stratified strata. That is your concave downward strata, and these are your unidirectional cross bedding. That is your cross bedded strata. So what I want to emphasize over here, that the same, if you try to correlate it three-dimensionally, then in a same place, in the same exposure, in some section, you may get some strata which are unidirectionally cross-bedded. But in the same exposure, in other section, you can take it as you may see it as a cross-stratified, trap cross-stratified. So unidirectional and trap cross-stratified may be in the same exposure. I am emphasizing, just see in a different direction in different sections. Why? Because the subaqueous dune, when they are flowing and when they are generating themselves, moving themselves according to the direction of flow. So along the direction of flow, if there is any such section, cross section along to the direction of flow, along the direction of movement of the dunes, or you may call it a ripple also. If it is like that, then you will get the unidirectional cross bedding. But for the same situation, if you have found some section which are a high angle or perpendicular to the direction of flow, then only you will get the trap cross stratification. So why I am telling you that in many instances we just tell that trap cross stratification is replication of the reflection of high energy level, and unidirectional cross stratification is not that much your energy level. It's somewhat less energy level. But from here you can see that no, with the same flow of energy, with the same energy level, just the direction of seeing, just the sectional plane that we are studying, if they will differ, your this stratification, that is your cross stratification or trap cross stratification, will differ accordingly. So this is my submission, that you please think over it when you will see if you can encounter it in field, anywhere, in any age. So cross stratification and planar cross stratification, need not to go to detail. Climbing ripple I already told. So it is upstream, it will be increasing, and in the downstream it will be increasing. Angle of climbing is increasing. Another thing is there, Hamoki cross stratification and heterolithic stratification. Hamoki cross stratification, you know, with the waves it is generating, and with the waves it is the formation of the Hamoki cross stratification is like this. Swells and hummocks are there, and with this mud drifts may be there at the crest or at the trough. May more often at the trough the mud drifts are there, and if this is the hummocks, it is actually for the wave or the storm wave. That is our yes is coming now, and with this yes you will be very sure with the combined effect of wave and current activity, some harmonic cross stratification will be formed here and there. So it is very important. So it will form just below the fair weather wave base. And heterolithic stratification, it is the it is your interlamination of your sand and shell or sand and mud like that. So there may be sand dominated heterolith, or it is called also pressure bedding. If it is mud dominated heterolith, it is also called lenticular bedding, when the lenticles of mud is there within the in the isolated ripples over there. So pressure bedding, isolated bedding, and directional data, you know, those diagram I am not going to this detail. So and last one is your gravity flow deposit. Gravity, the slumping or gravity deposits due to turbidite. So everything is mixing together there, and we are getting the grey wacke type of substance, and we are getting the matrix supported substance. So poorly sorted, random class. Just seeing under the microscope, we can tell that the sandstone is or the sedimentary rock is of from the gravity flow deposit or from the turbidite. So this is the gravity flow deposit. Just I am showing you. Hello. Any echo is there or not? Okay. Hello.
Yes.
Hello. Is it clear? My sound is clear or not?
Yes, sir. Yes, sir.
Okay. Some echo is going on. That's why. So in the from the Ib River coalfield, there at the our Monodi Valley coalfield, I have taken this captured this figure. So it is a gravity flow deposit. So a gravity flow must be there, but when how it has been formed, it is due to the slumping because very near there is a large fault system, and from that fault system the slumping starts, and ultimately it is stabilized as a gravity flow deposit. So it is a gravity flow. Now we have got there the truncated biomass series, not the total biomass series. So it is the total biomass series that just you see associated with the turbidite deposits. From the bottom, it is a massive granule to sand rapid deposition, then parallel laminated, and this is the cross laminated in the sea, then again the laminated seal, and again at the upper part it is the mud. It is the total sequence, but many of often we are getting truncated one. It is truncated up to C, truncated up to B after that. But one thing is very important about that the upper flow regime and lower flow regime. Two things are there: upper plane bed and lower plane bed. Upper plane bed is actually the static graphically lower plane bed, and the lower plane bed is actually the static graphically upper plane bed. Which is very much important. I think you can understand that in the upper flow regime, the sediment grains are parallel themselves, and they are giving you the upper parallel bed. And here, obviously for the high energy condition, but now the energy is decreasing towards top. Here is the mud, you can see. It's a very low energy precipitation, almost pelagic deposition precipitation. Here the laminated seal, it is the low energy condition. Here the low energy condition, that here it is the lower plane bed. But lower plane bed is static graphically the higher plane bed. Just you see as we are going details. How we can determine the upper plane bed? It is totally of your sand and sand. No intermediate lamination of shell will be there. But here shell sandstone lamination. That means the heterolith is coming over here. But here no heterolith. I can give you one instance. This is upper plane bed, Biomass. No, there is no low energy sediment is there. Cell is not there. So this is the upper plane bed. Now some indications, hole mark. I think you know it. I am not going to this detail. It will be taken later. So it is not a sedimentary structure. It is coming with this. That's why I am studying. So and the trace fossil at last. So trace fossil at last, you know, these are the trace fossils, this is colithos. So these things it should be a part of the sedimentary structure or texture because they are influencing the sedimentary horizon. We are here, we will get, what we will get from here? We will get from here a totally hodgepodge situation. That means a totally very poorly sorted because all things are mixed up together, and actually it is called a biochar zone. In the biochar zone, you will not get any stratification, anything. All these things are giving you a very poorly sorted. We have to see that whether this poorly sorted is associated with a trace fossil behavior or not. So this is very much important in that domain. So, and with last one is the Pcd structure, you have the penny-contemporaneous deformation structure formed along with the deformation and the solidification of the sediment. So some flame structure, some anti-dunes, that is your these convolutions, all these things are coming. Dewatering structure, slump and load structure. So your silicate part is over. Now the carbonate sediment, and after this carbonate sediment, just I will take 5 minutes break, and again I will start. I will finish today much earlier. I can tell you, so don't worry. So carbonate sediment and rocks, carbonate and these things I know these are known to you. So that's why I will need not explain these things. So silicate parts is over. Now carbonate, that is precipitation. In the two form, you know, either limestone or dolomite. Either pure CaCO3 or CaCO3 MgCO3 like this. That means dolomite. So yeah, chemical precipitation. The main processes are two types are there. Two main processes. One is biomineralization of CaCO3 by organism. Organism are taking calcium carbonate from the environment as they are growing, and from their growing situation, they are mineralizing the calcium carbonate in their body. So that is one thing, and another is the direct chemical precipitation. So calcium carbonate in the water in the environment, and that is just settling down according to the pH condition of the environment. So this is the very important thing, and biogenic carbonate formation occurs a wide range of organisms. Most organisms, coral, reef, that is the forams, algae, bacteria, you know. All those are the cells of your calcium carbonate. When they will die out, their cells will form this type of sediments over there. So coral reefs and microbial mats, stromatolite are example of more solid carbonate structure, and chemical precipitation produces non-skeletal carbonate, oid, pisoid, micrite, like that. So micrite and sphaerite, I am coming. So sedimentary, that is the precipitation, non-skeletal carbonate is a chemical, and the skeletal carbonate is the biogenic. So main two. And the sedimentary environment, that's also, you know, after James, that is a shoreward transport, is a subtidal carbonate factory. This is actually called a factory. All the things are over here, and subtidal, that is your organisms are over here, and when they will die out, or in the deep water planktonic, or their other algae or your foraminifer are there. They are the fallouts of the calcareous at the basin deeper part. So principal zones of carbonate production and accumulation, this is the production zone mainly, and this is the accumulation zone. So this is the two principal zones. Another zone is also there. I should take here, that is the seaward. When shoreward transport is there due to the current wave, then from here some depositional things, so that the subtidal carbonate depositional that has been carried over there in the seashore. So that is also a zone where it can be accumulated. And this carbonate sediment and rock, according to the carbonate shell, your oceans, marine shell and slope, all these things are there, where the fans are there, the reef has been originated. So it is a common picture, and it, need not to go into that detail. So carbonate sediment and rock, just if you see, it is the chemical precipitation, that is the non-skeletal. These are the non-skeletal. This is called oid. So oid, pisoids, peloid, these things are there. So according to the diameter, so oid is less than 2, pisoids is greater than 2, peloid is less than 1, oncoid is greater than 2 millimeters. So these things are there. So it is and it is called the intraclass. So this is one of the microscopic photograph of the oils. So these are the carbonates that are the non-skeletal carbonate grain, and this is rolling. And if it is rolling, it is actually called oolite also, oil or oolite. So carbonate oolite. So this is when it is rolling, and there is a nucleus over there. So over that nucleus, it is growing and growing and growing when it is rolling on the surface. So each and every time, through algal mat or through some sediment, it will collect carbonate material, and it is growing up. So it is the oil and pisoids. So now carbonate sediment. Now the classification of carbonate sediment. Classification means it is carbonate sand usually consists either of the skeletal elements or non-skeletal. Carbonate mud is commonly the product of the chemical precipitation, and carbonate sand, it is called the sparite. It is actually the from the non-skeletal. It is the skeletal remains, very fine skeletal remains. So two types are there. One is micrite, one is sparite. So texturally, the subdivision is like that. Number of classifications are there. Just you see, I am also not convinced which should be followed. Obvious is the last should be followed, which is, but still people are following the earlier ones according to their observation. So allophones and autochthones, which is coming from the different sources and which are growing there and binding together. So this is the allophones and autochthones after James 84 and Embre and Clovan 1971. So this is their classification. So carbonates, I need not go. Another one, this is very well documented. That is the intraclass, oolite, ossites, and pellets. Accordingly, when it is the cement is the calcite cement, it is sparite. The total thing is sparite. When it is mud, it is totally sparite. It is totally micrite. So it is intrasparite and intraclass are there. Oosparite, class are there. If it is micrite, mud is there, that is wood micrite. So accordingly, the naming is there. And if there is lithic fragment, it is dysmicrite, and it is reef rock when it is biolithite. The biolithite. So naming are there. Again, Fock's textural classification of carbonate sediment. It is after Fock 1959, and it is developed further by Kendall in 2005. It is now going on very. I think those who are familiar with this things, they can tell that which one is the latest, because what I have got is 2005. Possibly it is followed by many people right now. So over, because it has considered so many things. Over two-third matrix, micritic matrix, over two-thirds sparite matrix cement. So all these things, and according to the percentage also, percent allocates 1 less than 1, 1 to 10, 10 to 15. So these things has been taken into considerations, and the names are also varying like that. So according to your anyone who is studying that, according to his petrographic observation, he can tell that this should be followed and the name should be like this. But the basic things is same. That is your sparite biomicrite, or your packed, or your poorly sorted, or your rounded, or this micritic, totally sparitic. These things are different and different, and it is followed in different classification. Now the last one, modified Dhanam classification. It is also like that. That taking into account this Kendall also. So this is Dhanam classification. So different things are there. I am not going to this detail. Mud stone, wake stone, pack stone, grain stone, float stone, root stone, bound stone, battle stone, bind stone, frame stone, and crystalline. So these things are there, and according the size of the limestone, that is a mud, wake. That's we are having our very fine, medium, is your coarse, very coarse sandstone. Accordingly, it is also classified like that. So that is a limestone, and after the modified Dhanam classification. So the carbonate rocks may be classified like this, and I told you earlier that besides the siliclastics and carbonates, the less than 5% part is covered by some your these evaporites and other precipitates. So evaporites are very important from our point of view of the of our minerals and our industrial purpose also. So just you see one information that if we will take 1 kilometer of seawater, that means thickness, it will give you 12 meter of evaporite from that. So 1 kilometer volumetrically seawater will give you 1 kilometer of volumetrically means 1 kilometer thickness. It is not the volume cc or like that. It is liter or like that. 1 kilometer of seawater is giving you a thickness of 1 meter of evaporite. Now different types of evaporites are there, calcium carbonate, mainly calcium sulfate, gypsum, anhydrite, halite, and other tested ones are there. Now you can see that in a marine evaporite, the main one is your sodium chloride or halite. So this is the maximum, halite is maximum, then sulfate is there, carbonate is there, and after this halite, this is also halite, it is sodium halite, it is potash halite. So after NaCl, it is KCl. The most part is given by these halides, and this calcium carbonate or sulfate are less. So this is the main important. And with this 5%, that evaporite is one of this 5%, and within this 5%, another is your this volcanogenic sediments and rocks. The bombs, lapilli, pores, fineness. So ash, lapilli, bomb, everything is there according to their size variation, and we are getting the consolidated sediments in the form of fine tooth, coarse tooth, lapilli stone, agglomerate, volcanic breccia like this. So when these are associated with in the sediment, in the volcanogenic sediment, these are called volcaniclastic or volcanogenic sediment, and it is also a part of the of our lithosphere, and it is also part of our land part. So mineral grains, lithic, it is divided into three compositional part. Mineral grain, what are the mineral grains there? What are the lithic fragments there? And vitric, that is the volcanic glass or pumice over there. So these things have been delineated, and now we are shifting to another. This is the last part, and may I take 5 minutes, and if there is any question, you may please ask me in between, and then I will go to the last part. So any question, please, and if you will consider, I will take 5 minutes for them. So Bharti, Omnath, and Samsundar. So what should be done? The questions may be asked, but questions may be asked at the last part also after finishing it. Whatever you may suggest.
Sir, you can take, sir, for 5 minutes break. Issue.
Okay. So if any question will be there, that will be discussed after. No problem.
Yes,
Okay.
sir. Yes.
So okay. Then I am taking a 5 minutes rest, and after that I am coming back. Okay.
Yes.
Okay. So and this is the last part. Then I am going to take, because all these different types of sedimentary rocks, they are now finished, and not going to this detail because you know these things better than me. I know. So and now we are going to the provenance and tectonics afterwards. So after this, I am just give me 5 minutes. Okay.
Yes. Yes.
Okay. part that we know that what to do with all these analysis and with all these classifications, these things are there. And mm, now we want to know the provenance, we want to know how the sediments have been carried, what are the agencies, what are their hydrodynamics, and where they are now deposited, and what is their past history before deposition. So all these things will come out from here. So sandstone spectrography is widely considered as a powerful tool, you know. Now, about the mineralogy of the sandstones, the sandstones are detrital, you know. So they have been related to the major provenance types such as stable ketons, basement, uplift, magmatic arcs, and recycled ordnance. So the sediments are coming from each and every region, and obviously, if we follow them properly, then from which provenance it has come, it will come out. So that is our motto. So to identify this provenance and tectonic setting, recalculated parameters of Hoek 1980 and Dickinson and Subject 1979. It is plotted on a standard ternary diagram. Just I am showing you. This is the diagram. What happened? Which, before going there, which we want to, what we want to do, we want to know the provenance and tectonic setting. So provenance and tectonic setting, after this Dickinson and Subject 1979, now three vertices are there, you know. QT, it is written here, QT is your total quartz grain, QT is total quartz grain, F is your total feldspar, and L is your total lithic fragments. So accordingly, when it will be plotted, it is just, you see, it is recycled orogenic, dissected arc, transitional arc, undissected arc, all these things are there. Basement uplift, and is a craton interior, transitional continental. So these things has been, this tectonic setting, you know that tectonic setting we apply for the granitic rocks where the different types of tectonic settings are there, and from the chemical parameters and from the analytical, that is your trace element and oxides, and from there we can determine trace elemental ratio, we can determine that in which category my granitic rock belongs to. So in the same way, for the sedimentary rocks, these parameters are very much important. These quartz, feldspar, and lithic fragment grains, and accordingly, this classification has been done. Now, two figures are there, left one and right one. In the right one, you can say that all the things are same. Which has been changed? Now, QT is here. It is QT is the total monocrystalline quartz. It is named as QT, but it is wrongly represented here. It should be. It is actually, it is my fault. It is actually QM FLT diagram. The vertices is QM. QM means it is not QT. Just change it afterwards. So it is the total monocrystalline quartz. So it is very important. The left figure, it is total quartz. Right figure, the top vertex is the total monocrystalline quartz. F is okay, total feldspar, plagioclase and potash feldspar, and L is the lithic fragment and total lithic fragment. All these things are same. Only the vertex is different. QT and QM. Just you see the difference in the plots. The plots have been changed. The green one, recycled orogenic. It was in the left one, it is like that. Right one, just you see from the total right, this triangle, right side of the triangle, it is covered on already, and the positions and the proportionate positions of these diagrams have been changed over here. So afterwards, after QT, Dickinson and Subject thought that no, in the total quartz grain, we are also calculating the polycrystalline quartz, and polycrystalline quartz may be a part of the lithic fragment. So that's why it is better to take the lithic polycrystalline quartz in the lithic fragment, polycrystalline quartz in the lithic fragment, and to separate the quartz as only the monocrystalline quartz. So the shape is like this. So this is very important to if we can plot, we can get the tectonic setting and provenance from that. I am giving you one by one diagram, and I am telling you one thing, that if anyone from you want to publish a paper in the international journal about this grain size analysis, and after that this your provenance and tectonics of the sedimentary rocks, you have to follow it, you have to calculate these things, and it is not very tedious job. You can calculate it easily, and you should you should represent it in your paper. So this is very much important. That's why I am taking it in the last session. So again, provenance and tectonic, what are there? It is there QR, QT, that just you see the vertices, 4 diagrams, QT, QP, QM, and it is also QM. FL, it is the first one is FL, just the second one, this one, LVLS. This is FLT, and this is P and K. So different. What are these? These are, once it is QTFL, F is the feldspar, L is the lithic fragments, QT is the total quartz, including monocrystalline, polycrystalline. Once you are including polycrystalline quartz in here, you will exclude it from here. So this is the thing. So next is the QP. What is the QP? Just you see here, polycrystalline quartz chart and quartzite. So here QT is changed by QP. And what are these? LV and LS. LV is the volcanic lithics, LS is the sedimentary lithics. So these things are also made different. So lithicas there, whether they are volcanic or whether they are sedimentary. Why? Because we are having some earth orogen series, mixed orogenic sands, where we know in the back arc basin, in the fore arc basin, that is in the subduction complex zone. In the subduction complex, the day before yesterday I told you, when all these sediments are deposited together, then one should not use this diagram there, because here all the lithic fragments are taken together, but whether in that fore arc or back arc, we know both the volcanic clastic sediments are also there. So we have separated the volcanic clastic and only the sedimentary clastic. So these are different, and it is the QP, that means polycrystalline quartz. That means it is also from the lithic fragment. So what happened here? So we know the polycrystalline quartz is mostly given by your older metamorphic rocks, and after that your just a big gap in between, and after that polycrystalline quartz is also given by the modern igneous rocks. So if this is like that, then here this is one ordinate, this is one ordinate. So total lithic fragments are separated out, and based on the lithic fragments, these things have been done. So this is very important. Then again, QMFLT. LT means total lithic fragment. QM, you know, monocrystalline quartz. So here now it is monocrystalline quartz. Now the total feldspar and total lithic fragment. Just you see that the different observations are there, and these have been done, you know, as thousands and thousands of sediments have been calculated and have been projected in the diagram, and after that only they have come with this decision. So this is very unique, and we can use it everywhere. So now the next one is QM, monocrystalline, P and K. Just you see over here, there is a difference in the last diagram. Here feldspar has been differentiated, plagioclase and potash feldspar. So increasing ratio of plutonic to volcanic sources in magmatic arc provinces can be delineated from here. K is coming from your this provenance, and that is your inner arc provenance, and your plutonic variety is giving your Diagenesis. So this is also a very important part in that domain. So please bear it in mind. So provenance and tectonic setting can be put forward by the simple diagrams, and just excluding and including one in different vertices. This can give different connotation. Now, other tertiary ternary plot. What is that? QP. QP. That means polycrystalline. LVM, volcanic and metavolcanic lithics. Just you see. LSM, sedimentary and metasedimentary. So all the metamorphic varieties also are taken into consideration here, and you can see that rifted continental margin, then mixed magmatic arc and subduction complex, suture belts, very important. It's a great work done by that time. So in the suture belt, all this the metasedimentaries are also coming. With the metasedimentaries, the early volcanics which are now metamorphosed, the metavolcanics are also coming. So in the future belts, what happened? Your that recent the recent plutonic variety is also there. That means volcanic variety may be also there, and ancient volcanic variety is also there. So all that has been clubbed over here. Now here LM, that means your metamorphic lithics, LV volcanic lithics, sedimentary lithics. So lithics are lithic fragment are different, and we can try it for our consequences, our examples. This is very much important. Discrimination of tectonic setting, and you may move into very detail if you plot it your data in these diagrams. Now coming to the some bivariant diagrams and divariant also. First, it is the provenance and tectonic setting. This is here we are using the oxides, the analysis of oxides from the sedimentary rock. We are normally we are using for the igneous rocks, that is bivariant diagrams of oxides. Here also we are using the oxides. Now oxides, it is there, just x-axis SiO2, y-axis K2O by Na2. What it is giving you, there is a difference between oceanic island, active continental margin and passive continental margin. Day before yesterday I told you that active continental margin may be ultimately, it will be joined together, and it will be ultimately give you a passive margin. So now if your data says that you are talking about a passive margin, but your data are falling exactly, this has happened here. Your data are falling is the active continental margin. So from passive margin sedimentary rock, that is a sandstone, we are getting the components from the active continental margin. That means it is recycled. That means your data that it is showing now passive, but earlier it must be some component of active. But this is the beauty of it. So it is very important discrimination diagram. Then some direct diagram is there. Fe2O3 MgO, marine and non-marine deltaic sandstone. It is also very important for the seashore position, and non-marine and marine deltaic also the same figure. That is the same from same paper. MgO, Fe2O3 and SiO2Al2O3 triangular diagram. It is also there. So here they are considering Fe2O3 MgO. Now it is some advanced. They are also talking about your this SiO2 by Al2O3, because it is very important that the rocks over there, the sediments over there are very much rich in SiO2 by Al2O3. So that's why it is very much important in that domain. Now, log SiO2 Al2O3 and log Na2O plus KTO. Just you see, quartz arenite, subarenite, subarcose, leach arenite, another very important domain to give you that we are going to a turbidite sequence or not. So mainly in turbidite sequence, this type of diagram has been used. It's very much important. Chemical classification based on 1973 to Petillon. Now ternary diagram, it is all black, Fe2O3 MgO. So different oxides are being used, and different these your connotations are coming out. SiO2, and with this is L2O, Na2O, That is the semi-arid to arid. Increasing chemical maturity is towards this direction, and we are going from the arid to humid or semi-arid condition. So semi-humid condition. This is also done. And another thing, it is we are ACNK diagram we used in our metamorphic diagrams. So this is also like that. Al2O3CO, Na2O, K2O, ACNK diagram. Average UCC values is over there. Sorry, average UCC value is over there. And what happened? This is the average UCC value, and this is upper continental crust value. And we are saying that our rock is having this mectite or elite. That means these clay minerals which are far apart from the UCC. So it is not derived from the upper continental crust. Possibly it is derived from the lower continental or middle continental crust in the subduction zone. So this is very important in that domain. So that can be done. Just a minute. Here later. So and this is this diagram, you know, CIA, that is the chemical index of alteration. So moderate, low, and high alteration domain may be worked out from there. Al2O3. So for the sedimentary, not only for the sedimentary, but also when you are working, I have used this in my one of my paper for the bauxite generation. In the bauxite, there in the lithic profile, that is your soil profile over there. It is also very important for the chemical index of alteration to use it. That is from which actual provenance you have got your bauxite, whether it is from your granitic provenance, or it is your the basic ultra basic provenance. So it is very important in that domain. So this is one. Next, another one is UCC. Over here it can be delineated. So everything is written here after Garrels, Mackenzie, and here what the sedimentary properties, that is discrimination function. Two different discrimination function are there. I have not given here because it is a something by this. So it's totally, it is very large one. It is also very large function. But when you will go through this paper, you will get these functions, and you can put it. You can get the provenance, from which provenance your data has come. Now, another one, these are also very important in sedimentary rock, as we are using in igneous and metamorphic rocks also, the elemental ratio data, the trace elemental ratio data. Just you see the thorium by scandium in this, and chromium by thorium in this direction, and we are getting, this is the trend, this is the felsic input trend, this is the ultramafic input, mafic input. Which trend is there? Now after getting plotting all these things, we are getting the main trend is this. So this is the felsic input. Some ultramafic input is going on, but not that much. It is totally haphazard. So our main trend is this, and we can take that the felsic input is there. Cross plot, it is the strontium by magnesium. Strontium by magnesium, it is also given in abiotic and biotic. This is the in which domain it is going. It is the this, why this is the magnesium. This magnesium is coming from the this abiotic. It is not from a biotic. That means not from any calcium that has been replaced by dolomite or replaced by magnesium afterwards. And here the strontium given here, it is the it is the it is used in place of calcium. So strontium, you know, it is mostly incorporated into calcium, as it is called the diadochi, or it is called the similar ion in your that radius and mass is charge is same. So that is very important. So we used here strontium instead of calcium, and our strontium magnesium value told that no, it is a totally abiotic, not biotic. So these very important diagrams, just you see that thorium by scandium, zircon by scandium. So this value indicates that this a trend is there, compositional variation, sediment recycling and zircon concentration. So if this type of trend we can get, we will, that means it is not like that, not like that. It is meanwhile it is in between. So if it is like that, it is upper continental crust is here, and it is giving you that the it is a recycling trend is going giving. So thorium by lanthanum by thorium, lanthanum by thorium by in x-axis hafnium. It is the triangular plot lanthanum, thorium, scandium. All these diagrams and their references are giving here, and it is very important to delineate now if you want to publish your paper in any international or good national journals. It is very much important, and it is also important to know that exactly from which provenance your data has come, your sediment has come, and which tectonic setting it would be like. So, and it is very high resolution study. So, andesitic, just you see, mixed volcanic, it is here, the mixed felsic and mafic source. Only felsic isolated island are. It is passive margin source, and it is andesitic island arc source. So these things can also be done. If our trend is like this, we can safely tell that we are going to a passive margin source. So before the passive margin source, here the felsic, mixed felsic and the mafic, that is the andesitic mafic, these things are mixed together. That means we are more towards a foreland where which has been now converted into a passive margin. So this is very important in that. Just you see here, thorium by lanthanum, samarium by lanthanum. Here also thorium by lanthanum, samarium by lanthanum. The same figures, same thing. What it would suggest? These are the left one. It is the plot of bulk sediment. Left one. Right one, it is the plot of tephra glass composition. So only glass composition are plotted here, and total sediment, bulk sediment is plotted here. Why? This is the arc volcanism. So when we are doing this, we just you see the similarity. The glass composition, it is giving the same different arc trend, and our bulk composition is giving this trend. That is the upper one. That means this one. It is not giving this trend. Got it, I think. So this trend is absent over here. But this trend is present over here. That means our in that sediment, this arc volcanism, it is called here Honshu arc or like that. So this arc volcanism has given you the sediment supply. So that is very important, because in our Andaman arc also, Andaman cover in there also, we are having a number of arc systems parallel to each other. So from which arc these things has been volcanism has been the sediment has been derived. So this is more high resolution study of this coming from this your elemental, that is a trace elemental ratio study. So this is one. And now again an oxide provenance. I have got it later, so I have added it. SiO2. This is Roser and Kors. Roser and Kors 1986. K2O by Na2O, SiO2 by N2. Just you can see PM is the passive margin. So our data is concentrating. The data is concentrating over here. It is not over here. ACM means active continental margin. Just you see ACF active continental margin. This is ARC2, ARC1. From nowhere the data has been derived. Now the data is there from the passive margin over there. So this is very important. Another this three triangular system. It is thorium, scandium, zircon by 10. So continental arc, oceanic arc, everything we can delineate it from there. So these are very important plots, and you can use it according to your data. So these things is over provenant and tectonic. Now Another part is there, heavy minerals. As provenance indicator, all of we are knowing that which heavy minerals are indicating which environment. Now, the main heavy minerals are if we plot them according to our volumetric data of this heavy mineral after separation, what happened? Now, one data has been plotted. You can see that here the opaque mineral is the largest. Then coming the garnet. Then coming your zircon. Then in is your tourmaline. So obviously these things, then rutile. So these things are coming. So histogram indicated the dominance of opaque. So if we plot it like that, you know that which should be the maximum like that. The result obtained from the statistical study give clues regarding the provenance as well as the length of transportation and mode of deposition. Because we know that heavy mineral will sustain the transportation energy, and it will be concentrated in the latest part of the last part of the sedimentary pile. So that is the very important thing. So we know that there are these things are there, A, B, C, D, E. I have given the figures also. Zircon, tourmaline, apatite, hypersine, rutile, garnet, andalusite, sedimentite. These are the major heavy mineral that we can study under microscope, and we can go for the provenance detector. These are actually called provenance detector. Now, with this provenance detector, one thing is very important, that which are the main. Garnet obviously the main. Okay, no problem. But there is an index. This is actually called zircon, tourmaline, rutile, ZTR index. Now, what is the ZTR index? Going to here. ZTR index. Okay, I am coming later. Just provenance indicator. It is you know this. Still, I am telling. Garnet, stodolite, kyanite, selemenite, zircon, rutile, selemenite. They are dominantly medium to high grade metamorphic. Tourmaline and epidote, low to medium grade metamorphic. Stodolite, epidote, dynamothermal metamorphism. It is very important. As stodolite is coming, it is coming under your thermal metamorphism. It is dynamothermal because the metamorphism is caused by either thrust or some strike past of one another in any suture zone. That means in a shear zone. So, dynamothermal metamorphism is very important. Yellow brown tourmaline is a metamorphic source, just you can tell. And prismatic grains with greenish blue type tourmaline, brown colored tourmaline, they are from granite and pegmatite surface. Purple garnet, medium to high grade, all of you are knowing. Stodolite, kyanite, garnet, obviously medium to high, amphibolite facies zone. Opaque minerals like chemical indicate chemical leaching. It is from the crystalline igneous rock. Okay, opaque mineral. You have seen here that some opaque mineral, it is the maximum. It is coming mainly from the igneous, acidic and basic both. So there are different implication for the provenance. Now we are telling about the heavy mineral. These are ZTR maturity index. Mineralogical maturity of the heavy mineral assemblages is quantitatively, all those are qualitative, that we have determined earlier through microscope and through their abundance. Now, ZTR index an absolute measurement of mineralogical maturity of heavy minerals. It is the percentage of the combined zircon, tourmaline, and rutile. They have been calculated to 100%, and then they will. And after this, when if we are get all these things, and they are having their different distribution. Now from there, zircon, tourmaline, and rutile is worked out, and this is separated out, and these have been calculated to 100%, and that will give you the ZTR index. ZTR index is immensely important mineralogical maturity, and if the sediments are immature, obviously ZTR less, and ZTR is a determined omitting a micaceous substance, it has to be excluded. Okay, that I had already described. So it is a very good indication of the provenance indicator and the maturity indicator. So after that, the different categories of zircon. Zircon morphologies is very much important. Just you notice over there that what are the normal zircon morphologies? I am telling you one thing, because sedimentary basins, in each and every sedimentary basins, sedimentary rock and the sandstone, we are having zircon. So zircon, what happened? This is a very hard mineral. Hello? Huh. I am audible? Am I audible?
Yes, sir.
Listen.
Yes,
Okay,
sir.
okay.
Yes, sir.
So just you see, I am not going to this detail. The different shapes of zircons are there, and different overgrowths, and their rims, their rhythmic alterations are there within the zircons. So that's why it is very much important for from our this metamorphic study and our tectonic study of everything, and age determination also. Different layer is giving you different age and different tectonic history. So it is there. So okay, next. So different categories of zircon morphologies are there. Each and every zircon morphologies are giving you different. I am giving you the thing so that you can get it from here also. I am not delineating these things. So you can get the different implication for that. And last of all, I am telling you that petrology of rock is incomplete with petrography. So try to indulge on the petrography itself. As the lecture is on sedimentary petrology, I am giving this instance that the paper is there, the eye of an petrographer, the mind of the petrologist. Normally in each and every lecture I used to tell it because it's a paper by Peter Robinson in American Mineralogy 1991. You please go through it because after seeing an petrography, we can imagine ourselves that what to do with that and what should be our mind with there is there to go for the origin of the rock to catch it from the origin and up to its deposition, and what are the processes within that, what are the changes, and how to give the justification to the rock. So petrography and this petrology is obviously should go hand in hand, and it is very interesting that every petrologist should have a very good petrography guide. So thank you. Thanks a lot. So I have ended for the hello.
Yes, yes, sir. Yes, sir.
Okay, it's sent.
Yes,
It's sent.
Okay. So, anyone having any doubt or any question, then they can ask. They can interact with sir. Sir, there is one question in the chat box.